see what to take a like NLP technique to represent what to a vector use graph neural network like it use deep purpose. We will talk about it later in this video. So here are some examples of graph data. So we can represent image as graph like each pixel for node and there will be an edge between them if these two pixels are neighborhood of each other. So here we can see this pixel maybe it content of this this person and into this content this person like that. These are nodes and there will be connection between them if they are neighborhood like these fours can be represent these four pixels can be represented as these four nodes. Similarly we represent whole image like this social network like it can be we call Facebook and it can also be Instagram like these both are friends or maybe this person follow this person and this person follow this person. So there will be likely form a connection between these two. So they, that will become a like link prediction problem. We can represent text as graph also. Like if you say I am going, each word will be represented as graph. Each word will be represented as node and there will be an edge if these two words are very similar or you can say nearer to each other. Like here if you see these three nodes, let's say this is I, this is am, this is going. From I am going. So that's how we form text graphs, molecules. let's say molecule 1 is, it can be of one phenol, one paraphenol or something like that. So well, and it contains molecule 1 and molecule 2. So, and it is seen that all sweet animal contain this molecule and this molecule. So non-orange contain, orange is citrus and orange is sometimes sweet, and it contains, let's say, this molecule and this molecule, and it is seen, citrus element contain this molecule and maybe this molecule. So similarly, something is connected to sour and this is connected to this molecule and this molecule. Likewise, you have seen it form a graph, like this form a graph like structure. So you can convert this data into the like a graph, and after that you can use to mine some data, or you can take idea of new recipes, and in future it can also be used for like herbal medicines, like to discover herbal medicines, like can be useful for future Ayurvedic experiments. So drug discovery, protein interaction. Protein interaction is also a graph. Like here you can see all the nodes are of proteins and they are of 1 to 0 to many connection between them, like edges between them. Here you can say 2 to 3 edges, and here between these two you can say 0 edges. So it will clearly form a graph when we consider protein interaction, like if this protein somehow affect this protein, there will be an edge between them. So likewise it will form a graph. Here you can see like four color, a graph containing four color. This is another problem, like finding subgraph or community. Problems with graph. Graph didn't have any inherent order. Like every time you start algorithm, um, you are not like you every time you start algorithm means graph neural network algorithm, there is no guarantee that it will start with the same node. Like when you start first time, it maybe start with this node, but in second time when you start the graph neural network algorithm, it may not start with that node. It may start with this node or maybe some other node. So there's a problem with graph every time, like I said. So we need architectures that are not affected by node order. Let's see how graph convolution network handles this. It's adjacency matrix. You know adjacency matrix, like every graph can be represented as adjacency that, like for all the nodes, we get this initial embedding. Let's say using diagram forms. So, and in graph neural networks, it contains three principles like message passing, aggregation, and update. We will see for node 1 how this works. For node 1, its neighborhood are node 2 and node 3. By aggregating, like our aggregation function, which is a hash function, which is somehow in like aggregate these three embeddings, like somehow embed these three embeddings. And in updation phase, it will update like h1 of k to h1 of k plus 1 like this, which will contain some information of node 3 and some information of node 2, which is calculated by our hash function or aggregation function. For node 2, it is neighborhood of node 1 and node 4. That's why it contains information of node 1 and node 4. So, but in the case of node 3, it is only neighborhood of node 1. So, that's why it's only contain information of itself and node 1. So, that's how in the first graph neural network layer this will happen. In the second pass, or in the if we use a second layer of graph neural network, then this node force information may contain in node 1. Like how, like we have seen, node force information travel into node 2 by a one pass. Now the aggregation function will apply on these three embeddings. So if our aggregation function find this information to important, so it can contain like update nodes 1 embedding, like adding this node force information from node 2 to here. Graph convolution network is a semi-supervised graph neural network for classification. It is spectral based CNN means it exploits eigenvalues and eigenvectors of adjacency matrix. Like you know adjacency matrix, it is an n cross n symmetric matrix. Like n cross n means if it contains n nodes, it will have square matrix of n, and it also is symmetric. Like let's draw for you. Like this is the matrix cross, and this is node 1, this is node 2, this is node 3, here also 1, 2, 3. If node 1 is connected to node 2 and node 3, like that's why there will be 1 and other will be 0. Here node 1 is connected to node 2 and node 3, other will be 0. Node 2 is connected to node 1 and 4. So here let's say 4. Here will be 1 and other will be 0. Likewise, it will form matrix of symmetric like we have seen. normalized graph neural network architecture. Yeah, like we have studied before, work to have present, which is deep work based means like let's say you have this graph like I and then and he is going going like when you consider of deep work like I is embedding ice embedding will more equal to R than he because I is nearer to R. Like if we travel like this, it will pass encounter R after that going and after many time it will encounter he. So I is embedding will more closer to R than he. That's how deep work based embedding work. So, theory behind graph convolution network. In the paper, they initially have the idea like apply some filter like convolution in computer vision like g theta into x node which is node feature matrix like g theta into x equal to u into g theta into u transpose into node feature matrix. We do Fourier transformers to our filters. So where u is the matrix of eigenvectors of normalized graph Laplacian L. You may find some difficulty in here. It will completely okay if you ignore this and I will mention something you only have to remember that. So where U is matrix of eigenvectors of normalized graph Laplacian. Normalized graph Laplacian. What is graph Laplacian can be considered as I minus d to the power minus 1 by 2 a into d to the power minus 1 by 2. A is adjacency matrix and D is degree matrix where equal to U into lambda into U transpose. We call normalized because of this. When you see the formula of Laplacian or you can say graph Laplacian, it will of I minus D I, min, I minus like adjacency matrix I minus A. Computing eigenvector is expensive and more eigendecomposition is also expensive, but eigendecomposition is well approximated in Chebyshev polynomials of order of dk of x up to kth order, which is a recursive algorithm like we will see. Now it will represented as g theta dash into lambda because instead of x we consider instead of this x we consider this lambda like we apply to this. It's nearly equal to summation of k equal to 0 to k theta dash k dk of lambda tilde where lambda tilde is considered as 2 by lambda max into lambda just eigenvalue of L. And the Chebyshev polynomials is recursively defined as tk of x equal to x tk minus 1 of x minus tk minus 2 of x with dx d0 of x equal to 1 d1 of x equal to x. So our equation will become g theta dash into node feature matrix will be summation of k from 0 to k theta dash k tk into L tilde into x. So instead of this k we apply this L tilde. We apply to this graph Laplacian. Let limit k equal to 1 for Chebyshev polynomials for computation is, but it's still hold rich information since we use multiple filters, like we use more filters c theta dash, so it will be still be rich information. And also assume lambda max equal to 2. Like to eliminate this term we use like this scalar, we use lambda max equal to 2. Now our equation will look like g theta dash into x is nearly equal to theta dash 0 into x plus theta 1 into L minus identity matrix x. So here if you put like d of 1 which is dx dx is equal to x. So here will be theta 1 dash into d1 dash x, like d1 dash L which is here L tilde equal to graph Laplacian minus I. So here we apply this to x plus theta 0 equal to 1, so d so so d0 x equal to 1, so this will become 1, so theta dash 0 into simply x. So that's how we got this expression will be equal to theta 0 dash into x plus theta 1 dash d to the power minus 1 by 2 a into d to the power minus 1 by 2 into x. Like we have calculated here L equal to I minus d to the power like that. So here we have cleared this L minus I information as this d to the power minus 1 by 2 and into d to the power minus 1 by 2. So we apply it here, we put it into here. model in Gaussian layer, we have to calculate a tilde. After that, we use two layers, like they have used two layers of Gaussian graph convolution layer for classification. So they first use first layer they are considered a tilde and two node feature matrix and two learnable parameter W0. That is of one layer and its output passed into a ReLU function which is to produce the non-linearity. After that, its result is multiplied into L tilde into W1 and then it passes into a submax layer for its classification because it's a classification problem. So here W0 and W1 are learnable parameters. We can say words that would be learned during the training. Advantages of graph convolution network: captures graph structure, leverage the node connectivity and neighborhood information effectively. Like we have seen from it can really get its neighborhood information into this node by graph convolution network. So there's an advantages. Parameter efficiency: share weight across the graph, reduce the number of learnable parameters. Like you have seen here, by using two layers of graph neural network, node 4's information can be contained in node 1. So without explicitly containing an edge between them. That's how node sharing works. Like this information travel from here to here. So scalable to large graph, especially when using sparse matrix operation. You may have known, like we use a separate type of matrix representation for if there are many sparse elements. Like there are many zeros, it will be of size like non-zero elements cross 3. Like first row content non-zero elements row and second column content it's column. So second column contains non-zero elements column number and after that the non-zero element is 3. And if there are 5 non-zero elements in a matrix of 7 cross 7, it will be of 5 cross 3 in sparse representation. So for this type of sparse matrices, we define we define separate operations like to reduce the time complexity. Generalizes the convolution neural network to graphs. Extend deep learning techniques to non-Euclidean domain. Non-Euclidean domains you can say parabola, hyperbola, like that. These are non-Euclidean domain. So we can extend deep learning techniques like artificial neural networks to this non-Euclidean domain. Good for semi-supervised learning. Effective with few level nodes due to neighborhood propagation. Like we have seen, Gaussian is a neighborhood propagation algorithm. So here let's see we have this information like this. This is a graph which contains only two label nodes. It contains eight nodes, but it only contains label of two nodes. In the label propagation in first pass, it will label this node as L, this node as L, this node as R, this node as R. Because these two nodes are neighborhood of the label L node than the R node, so that's why these labels are L and these labels are R. In the second pass, it will also label these as L and these as R. So from here you can say from two label data you can contain the label of 8 nodes. So that's how it's become advantageous. Oversmoothing node representation may become indistinguishable after many layers. Like when you apply more and more layers, like we have seen in by applying two layers, node 4's information can contain in node 1. Similarly, if we keep adding the layers, there will be one such stage where every node contains the information about all the nodes. So it will be like node 1 contain node 2's, node 3's and up to node n's information, and node 2 also contain from node 1 to node 2 is up to node n information. So there will be not much difference between node 1 and node 2's embedding. So that's how it will become undistinguishable. Limited to local information. Standard graph convolution network mostly aggregate from immediate neighborhood. Like it only aggregate from its neighborhood. Maybe there are more there is a information which is in far node in the far node than its immediate neighborhood, but it's more valuable, but it cannot be used in the graph convolution network. Poor performance on dynamic graphs struggle with evolving graph structure with modification. Struggles with evolving graph structure with this is with modification. Like let's say we have this three nodes, this graph. Let's say we have this graph, and in pre-training we calculate this delta for these three, like these three nodes. After calculating a delta during training, let's say it's changed like this. There will be another edge and another node. So the graph changed, means it's dynamic in nature. So but in pre-training a delta, it only contains these three nodes information. So it will completely ignore this node and this edge information. Like if this is if this contains 3 cross 3, like if it is like 3 cross 3, this is this will become its adjacency matrix, and it will calculate a tilde on that, but it will completely ignore this, like this. After adding this, its representation will be changed like this. Let's use another ink. After adding this, it will become 1, 2, 3, 4, 1, 2, 3, 4, like 0, 1, 4 is only connected to 2, so 0, 1, 4, 0, 1, 0, and here 0. This is after adding this node and this edge, but it will only operate on this. So this is a problem. Difficulty in handling edge features. Basic graph convolution networks don't naturally incorporate edge attributes. Like in molecules, we have seen there are of different types of bonds, like single bond, double bond, covalent bond, valency bond. This type of information can be encoded as into edge feature, but in graph convolution network, these don't use any such type of edge attributes. So there are some disadvantages of graph convolution network. Graph neural networks are not new, however, the field remains relatively unexplored. Graph convolution network was one of the first models to bring convolution to graph. It considered as now a legacy architecture that paved way for many advancements. After coming GCN, there are a revolution unlike graph neural networks. Like there are many types of graph neural networks, like a graph sets, data attention network, and many more. So, but for the graph convolution network, they all are possible. So this is a legacy architecture. In today's world, where level data scarce, we rely heavily on self-supervised methods. So for the self-supervised method, graph structure data is great. Self-supervised or semi-supervised. We have seen semi-supervised version here, and in self-supervised we can cluster the graphs to get the embeddings, to get the labels. So this is great for the semi-supervised and self-supervised. Only a drop from the ocean of graph neural network has been explored and many to go. So that's it for today. Let's talk about some summary. First, we will talk about what is graph, and after that, we will talk some examples which can be represented as graphs. After that, we will talk about graph convolution, graph neural network, and how it's different from artificial neural networks. We talk about how gradient flow in graph neural network by three phases, like message passing phase, aggregation phase, and updation phase. After that, we talk about graph convolution network, and see some of its advantages and its disadvantages, and we see some conclusions. So that's it for today. In the next video, we will talk about graph sets. Thank you.